Welcome to this video on Introduction to Nonlinear Control, where in this video we're going to talk about some fundamentals covered in the first chapter of the book to set the tone, to cover definitions which will be necessary throughout the subsequent chapters and which will be repeatedly used. So let's get into the actual notation. The models we are going to be working with are predominantly state space models represented through first order differential equations. What does that mean? Well, it means we have a state x, and on the left hand side here we have the derivative, the time derivative of that state. X is a function of time, and then x dot represents the shorthand notation for d over dt. And on the right hand side we have a function depending on that state x, and then for matching dimensions f needs to be a function from Rn to Rn, where n denotes the dimension of the state. As a solution, or as a general solution concept, we assume here that, or we say that x is a solution of that differential equation if it is an absolutely continuous function that satisfies equation 1 here for almost all t. So it doesn't need to be satisfied for all t, and accordingly x of t doesn't need to be continuously differentiable or differentiable everywhere, but for almost all t. To guarantee that such a solution exists, at least locally, it is sufficient to assume that f is a locally Lipschitz continuous function. We will not go into detail with respect to that in this book and also in these video lectures here, and we will in general assume that the solution exists. If it is important, then one of course has to check that and make sure that the right hand side f satisfies specific properties. When you think about the dynamical system, you should always have this representation in your head, but we will predominantly use the shorthand notation. So x dot is equal to f of x, and then it is clear from context that x is a function of the time t. Here, equation 1 represents a time invariant or autonomous system, while if the right hand side f explicitly depends on time t, then we have a non-autonomous or time-varying system. So, of course, here the right-hand side implicitly depends on the time t because x is a function of t, but f does not explicitly depend on time, whereas here the function f additionally depends on time, and then that system is called time-varying. A third class of system we are going to look at is a system with external inputs. So either represented through x dot is equal to f of x comma u, or x dot is equal to f of x comma w. Meaning we have this external signal u or w. And there is essentially no difference between this representation, however, in the context of this book, and also I would say with a lot of publications, U generally denotes a degree of freedom, an input, whereas W in general represents a disturbance or reference signal. So U is something we can choose or design, whereas W is something we have to live with. And in that context, it is used here and often in the literature. As a last component of a system, we can add an output function, so y is equal to h of x comma u. And then we have the three components, x denoting the state, u denoting the input, y the output, meaning not all the states X might be available through sensor measurements, and only a subset is available, which is then captured through this output equation. Okay, how do we get a system representation like this, or where does a system representation like this come from? So, as an example, we can look at a mass spring damper system here, meaning we are interested in the position here of this mass here with a particular weight m, and we set our coordinate system so that this corresponds to the origin, and then we are interested in a displacement of the mass here, and the mass is connected to a spring. There might be friction forces, and there might be external forces we can apply to the system. Through Newton's law, then one can achieve that by summing all the forces. One can get a second order differential equation, second order, because here we get the second derivative of the position is equal to the sum of all forces, and the sum of all forces here consists of three components: the external force, the force from the friction, and the force from the spring. It's not in the representation we had on the previous slide, but we can transform it into this representation. Namely, if F is a force we can design, then we can denote that as U. This is a second order system, so we need to rewrite that into a first order system. To do that, we introduce a new set of variables. Here in this case, we define x1 and x2, and we say x1 is equal to y, x2 is equal to y dot, which is just a definition, which then means that if we take the derivative, then we get x1 dot is equal to y dot, and x2 dot is equal to y double dot. So from the first expression here, we can replace y dot and write x1 dot is equal to x2. We've eliminated y. And in the second equation, we can do the same, namely y double dot is given through this expression here if we divide by m, and that allows us to get a representation only depending on x1, x2, and u. And we have isolated the first derivative of x on the left and the function depending on x and u on the right. Meaning we can write that as, in this case, linear dynamical system of the form shown on the previous slide. And here we just need to remember, what were we interested in? Well, we said we are interested in the displacement of the center of mass, meaning we can define our output function in such a way that we have y is equal to x1. And a question we are interested in general, and what we will be covering in the following chapters, is, well, how does y of t, the output, the position, evolve over time when we are changing the input u, so if we are applying different forces here. And solutions we are in particular interested in are, for example, equilibria, meaning what happens if x dot is equal to 0? That would mean that x is not changing anymore. What is a condition for that? So, and that's by definition, we call a point or a state xe an equilibrium of a differential equation if it satisfies f of xe is equal to 0. And that means that at that point we have x dot is equal to 0, meaning the solution is not changing and is constant. If we are taking a time varying system, then this needs to be satisfied for all times t. So that's a slightly different requirement which needs to be satisfied for time-varying systems. In the case of a system with input, we can define an equilibrium pair, meaning an input u and a corresponding state x, xe, such that the right-hand side vanishes, and that again means with this particular constant input signal ue, we will have x dot is equal to 0, meaning our solution xe will be constant. And just as a simple quick calculation and a good exercise for you to go through, we can in general assume without loss of generality that the equilibrium of interest is equal to 0. And that can be done or achieved by a coordinate transformation, by rewriting x and introducing a new state simply through this translation here, and by defining a new function now of this new state z instead of x. By going through this calculation, we end up with a new differential equation, z dot is equal to f hat of z, and by design now this function satisfies f hat of 0 is equal to 0. And the only trick up to some extent that is used here is that the derivative of a constant, so xe is constant, is equal to 0. That's why this transformation, simply a translation, does not change the derivative. So z dot is equal to x dot. And if we go back to the mass spring damper system now, so if we wanted to check what are the equilibria of the mass spring damper system, so how do we calculate it? Well, we simply set the right-hand side equal to 0, leading to these two conditions here. From the first equation, we see that, well, it means that x2 needs to be equal to 0, essentially meaning that the velocity of the mass needs to be equal to 0. And from the second equation, if we plug that in, meaning using x2 equal to 0 here, and if we are not applying a force, then we also see that x1 needs to be equal to 0, meaning the equilibrium position is really 0. But if we would apply a different force, then we can actually move the equilibrium to an arbitrary position. And yeah, you can calculate how an equilibrium pair would look like, and how you can characterize that by finding the correct input u for stabilizing the mass at the particular position. The mass spring system is a simple linear system, but still interesting to analyze. And there are more complicated, more general systems that can be modeled and invested in their properties investigated. So one other example that is usually used for illustrations in academia is in the context of nonlinear control is the inverted pendulum on a card. So and that can be modeled as a general mechanical system where we have now a card with a particular mass, where we again look at the displacement of the center of the mass here of this card. And now we have an additional variable of interest, namely here the angle of this pendulum. And then we can look at two configurations, namely either the pendulum in downward position or the pendulum in upward position. Even though this is a rather academic example, it has also important applications. For example, this could represent a tower crane, stabilizing a tower crane, or in the upward position, it could represent a rocket. You have to stabilize a rocket, or for example, it could be used to model a Segway. Again, by modeling it here, we get a dynamical system with particular states, external forces, which we can again identify as inputs, and certain parameters. So as the last component here, we again have certain parameters, and as we've did it before, even though it is more complicated now, we can introduce the state vector by rewriting the second order system here into a first order system, and then get a representation of the form x dot is equal to f of x comma u. So this discusses the main terminology in terms of system dynamics, equilibrium, and definitions of equilibria, and how we can go from physics-based modeling to the representation of a dynamical system in the form x dot equals to f of x comma u. And then the next chapters will be, once we have our system in that particular form, then we can analyze its properties. Another important slide with terminology I want to go through is shown here, showing different classes of functions which have become quite popular and are used quite often in proof techniques and in presentations of proofs in papers in the context of nonlinear control. And these are class P, class K, class infinity, and L and KL functions. So it's really important, I would say, that you familiarize yourself with these classes of functions, because if they come natural to you, then a lot of proofs will become a lot easier to understand and potentially also to write. Okay, so what are these classes of functions? The first class we are going to need is the class of positive functions. So these are quite simple functions going from the positive reals to the positive reals. The class of positive functions is assumed to be a continuous function. It's assumed to be 0 in 0, but then strictly bigger than 0 everywhere else. So here an example is shown in this particular case here. The next class of functions we are going to need are K functions. So these are positive functions, but additionally they are strictly increasing by assumption. So this function here is not strictly increasing. It has a maximum over here. But then to the right we see two examples of K functions. 0 and 0 continuous, strictly monotonically increasing. Next class then is K infinity function. So we additionally require one additional property, namely that the function is going to infinity when its argument is going to infinity. So these functions here are strictly monotonically increasing, but converge to a fixed value, whereas the functions shown here grow unboundedly and go to infinity. The nice property of K and K infinity functions is that they are invertible, and that's used in a lot of proofs. So you can invert these functions and then, for example, rescale time through that inversion. And the inversion also preserves properties in terms of, if you have a K infinity function and you take the inverse of that K infinity function in terms of a mapping, then that's again a k-infinity function. Two more classes. Well, so the first three were, these two were monotonically increasing. Now we take another class, the class L functions. These functions are still positive functions, but they are in general, or they are bigger than 0 at the origin. But instead of monotonically increasing, these are monotonically decreasing and going to 0. And the last class are KL functions, which combine a k-infinity function with an L function, and the first argument a k-infinity function, in the second argument an L function. All right, so probably a bit too fast if you just see them for the first time on this slide, but as I've said, if you look at a paper published in Transactions on Automatic Control or in Automatica, then it is likely that you will find these definitions or some of these definitions in the paper, in the proofs, if it is on nonlinear control using the Lyapunov techniques. All right, and that's the end of this video lecture here. We have covered some fundamentals, and then from here we can move on in the next video to stability notions. For equilibria, for example, how do we characterize if an equilibrium is stable, unstable, asymptotically stable, or exponentially stable?